Hello students, I am Professor Varsha Patil. I welcome you for second video lecture for the topic titled Computing Similarity. And this is Unit 3 for the course titled Data Mining and Data Warehousing. In first video lecture, we started with learning the terminology. What is similarity? What do we mean by dissimilarity? Proximity is the term which is used commonly for both referring to both similarity and dissimilarity. And we learned how to compute proximity for nominal attributes. And in this lecture, we shall be learning about how to compute proximity for binary attributes. We shall learn for both symmetric as well as asymmetric binary attributes. Binary attribute has one of the two states, 0 or 1, where 0 generally stands for attribute value is absent or that attribute is absent, and 1 means that it is present. Let's take an example of attribute titled diabetic. And for some patient, say a patient named Hemant, if we conduct a test diabetic and then we have an outcome, that is measurement, as either 1 or 0, where 1 popularly indicates that patient is diabetic while 0 indicates that patient is non-diabetic. And another important thing which we need to remember or note is, for binary attributes, we do not use the measures, that is proximity measures, which are commonly used for numeric attributes. There are some special measures which compute proximity for binary attributes, and we shall be learning those. Proximity for binary attributes is measured by computing dissimilarity matrix for binary data. And this dissimilarity matrix is nothing but a 2 by 2 contingency table. And in this contingency table, we note down the values, which is nothing but total count for the attribute values, having values both 1, 1, both 0, 0, one of them 0 and the other 1, and noting down those values in this table, which we call as contingency table. In this table, we have two objects, object I and object J. And we are going to compute the proximity for these two objects. That is, we are going to find out what is similarity between object I and object J, or we shall compute dissimilarity for object I and object J with the help of binary attributes which are defining these two objects. And while doing this, we shall be computing how many attributes count is having for both object I and J values 1, 1. That we will note here, and which we refer as Q. When we compute both the values 0, 0 that are named with value T in this contingency table. And when value is 0 for object I and value 1 for object J, that is represented with the count S. And the count R indicates that these many are R number of entries for object I and J for binary attribute are in this way, that value is 1 for object I and value is 0 for object J. So here in this contingency table, these four values are important. So for object I and J, what we are going to count is, we'll count number of attributes having both the values 1, 1 will be named as Q, and sometimes in literature you will come to know that different variables are used for representing these values in this contingency table. We are using a notation which is commonly used in literature, and the book which we are referring, Hankamer's book, uses this terminology. So we are using, you can use any different variable. F11 is also used in literature popularly to represent this value Q, which represents nothing but number of attributes having both the values 1, 1. And similarly, F10, F01, F00, sometimes M11, M10, M01 and M00. And we shall be using this contingency table for computing the proximity. And here P refers to sum of all the four binary attributes are either symmetric or asymmetric. Binary variable is symmetric if both of its states are equally valuable and carry same weight. Example, gender. In gender could be male or female, and equal importance is given to all the records with having value either 1 or 0. Whereas in some cases, like a variable diabetic or some test for some health, like say COVID-19 test, it could be either positive or negative. In this case, equal importance is not given to both the outcomes, and more importance often in case of test of COVID-19 will be given to the values which are positive. So it is said that the relevance for both the values is not same in case of asymmetric, whereas it is equal importance in case of symmetric variables. We shall be learning how to compute proximity for both symmetric and asymmetric. Let us start with symmetric binary attributes. Dissimilarity for symmetric binary attribute is called as symmetric binary dissimilarity. And for computing this symmetric binary dissimilarity, say between the objects I and j, we compute it using formula dij is equal to r plus s divided by total of all the attributes, that is r plus s divided by q plus r plus s plus t. Recollect here that r and s were the values where either of them is 1 and the other value is 0, and this is total number of all the attributes, and it can be rewritten as r plus s divided by p because p represents total of all the variables. This is computing dissimilarity, and we can also compute similarity with the formula subtracting dissimilarity from 1. We have learned this in video 1. What is the relation between similarity and dissimilarity? Is similarity can be computed by subtracting dissimilarity from 1, or we can, if we compute similarity in other way, dissimilarity also can be computed, and it results in q plus t divided by p. If you look at now value q and t, recollect in contingency table, q represents both the values are 1, 1. This q represents that both the values are 1, 1. And t represents that both the values are 0, 0. How is this similarity ij is equal to 1 minus dij resulted into q plus t by p? Is just substituting the values. So if we substitute, then we get it as 1 minus, we substitute the value of dij, and when we rewrite it, then term r and s gets cancelled and it results in q plus t divided by p. So in brief, computing proximity for symmetric binary attributes is computing either dissimilarity or similarity. And for computing it, what we use is we use this contingency table. And from this contingency table, we compute distance between two objects I and j with the formula dij is equal to r plus s divided by q plus r plus s plus t. And similarly, we compute similarity and representing it as similarity between I and j is equal to q plus t divided by p, where p is sum of all attributes. So let us solve one example for computing proximity of symmetric binary attributes. So look at this table. We have 3 records for 3 persons, Jack, Mary and Jim, and there are 6 features titled test 1 to up to test 6. And these are symmetric binary attributes whose values are listed in the table. And we have to compute dissimilarity between each two objects, that is Jack and Mary, Jack and Jim, and similarly Mary and Jim. And to compute this distance between each pair of these patients, we shall be using our formula for computing dissimilarity. And for that we need to compute a contingency matrix for each two of them. And contingency table is nothing but count of having these features having values both 1 1 0 0 1 0 or 0 1. So let's do it. So this is our initial table. In this initial table, these are the given values, and let's construct contingency table initially for Jack and Mary. So how did this value Jack and Mary table values are computed? So from where did this 2 came? This 2 is nothing but value for Jack is also 1 and Mary is also 1. So here in this rows we will try to find out how many of the columns are having both the values 1 1 for Jack and Mary. So this is first one 1, then for test 3 it is both 1, so 2. So this is how we listed 2 here. Now to fill up this value, from where did this 0 came? So this 0 is nothing but value for Jack 1 and for Mary 0. So how many of them are having values 1 and 0, and there are no such values, so it came out to be 0. From where did this 1 came? This 1 is representing value for Jack 0 and value for Mary 1. And how many are such count? And the count is, we have just for test 5 value of Jack 0 and Mary 1. So it came out to be 1. And 3 represents both the values 0 0. So if you look at both the rows for Jack and for Mary, having both 0 0 is test 2, then test 4 and then test 6. This is why count is 3. And this is representing sum, row wise sum and column wise sum. This is for now. We are computing for Jack and Jean. Similarly, like the way we computed for Jack and Mary, we shall compute for Jack and Jean, and we shall also compute for Mary and Jean. These are the 3 tables for these 3 pairs. And from these tables, contingency tables, we shall compute their dissimilarity. So dissimilarity between Jack and Mary comes out to be, dissimilarity formula was, we are considering either of them 1 and the other 0. That is R plus S. That is 1 plus 0. So this is 1 and this is 0 from these 2 values, divided by sum of all of them. So it comes out to be 1 by 6, that is 0.16. And for Jack and Jean, we shall take a summation of 1 plus 1 divided by sum of all. And for Jean and Mary, it is 1 plus 2 divided by sum of all, which comes out to be 0.5. And when we fill up all the values in our dissimilarity matrix, the dissimilarity matrix for the given table comes out to be this. We have 3 objects, Jack, Mary and Jean, and this is a dissimilarity between each pair of objects. Every object, if we talk about dissimilarity, is dissimilar, it is not dissimilar with itself. So dissimilarity is 0, listed as 0 here, and these are the values which we computed. Now computing similarity matrix with dissimilarity. What we computed is dissimilarity. So from dissimilarity we can always compute similarity. That is our formula, which is similarity is computed with 1 minus dissimilarity. So this was our dissimilarity matrix from which we can always compute similarity between. And every object is similar with itself, so we get a diagonal values as 1 1. And we have learnt in earlier lecture, video lecture, that similarity and dissimilarity are symmetric, so we fill up only lower triangular matrix. This was proximity measure computation for symmetric binary attributes. Now let us learn how to compute proximity for asymmetric binary attributes. Examples we learnt: for particular test examination, student result could be pass or fail, and they aren't equally important. We do not give equal importance to some cancer test, whether it is positive or negative. So the attributes are said to be asymmetric binary attributes. So for asymmetric binary attributes, the 2 states aren't equally important. Given an asymmetric binary attribute, the agreement of 2 ones, that is both positive match, is considered to be more significant than both negative. If we are talking about, let's say, two patients, and we are trying to find out what is the similarity or dissimilarity between two patients. And we have conducted many tests. Maybe how much is the hemoglobin for the particular patient, both the patients, how much is their sugar test, then a BP, and so on. And for these asymmetric binary attributes, we are not giving equal importance when both of them are negative and both of them are positive. Rather, we look for all such attributes where both of them are having a positive test. We are not looking for such attributes where both of them are having a test as negative. This is why for asymmetric binary attribute, this T I have noted with a circle, a red color, that is having both the attribute values 0. And we have to note that in symmetric attribute, we were giving equal importance. So we were considering all the 4 attributes. But in asymmetric attribute, we are going to omit this T, which is both the values are having negative. This is why asymmetric binary attributes are also named as monary, because they are at a time we are considering only one important state of out of 2. The dissimilarity based on these attributes is called as asymmetric binary dissimilarity. And here we are omitting the value T. We are not considering the count of all such attributes where both the values were 0. So in contingency table, T was that particular variable, and this was the similarity formula which we used for symmetric binary attributes, and here this T we are going to omit now. So resultant uh, formula for computing dissimilarity between two objects R and S results as Dij is equal to R plus S divided by Q plus R plus S. Here T we have omitted. So asymmetric binary attributes dissimilarity is nothing but Dij is equal to R plus S divided by Q plus R plus S. And we can, just like in symmetric attributes, we can compute their similarity by subtracting Dij from 1, and resultant similarity comes out to be, after substituting values, cancelling the negative things, we get a formula as similarity for asymmetric binary attributes for two objects, say I and j, is computed as Q divided by Q plus R plus S. You must have noticed that at denominator T we have omitted, and similarly from numerator also T has been omitted, and Q stands for both the objects attribute count where both the values are 1, 1. And you have to note that this coefficient similarity Ij is very popularly known as a Jaccard coefficient. This name is because of the scientist who invented it is Paul Jaccard. So in brief, this is proximity measure for asymmetric binary attributes. This is for computing distance between the two, that is dissimilarity, and this is computing nearness between them, that is computing similarity between them, and this is nothing but Jaccard coefficient. And I spent some time in reading something about Paul Jaccard, by whose name we call this popularly used similarity measure as Jaccard similarity coefficient. So I read some literature and I came to know that Paul Jaccard was a professor of botany and plant physiology at Duke. He developed Jaccard index of similarity and published it in 1901. He has introduced use of species to genus ratio called a generic coefficient in biogeography. It wasn't easy to understand all these terminologies and what is this biogeography. But still I referred little more reading literature to read some additional things about what is exactly his research and how we are using that research in data mining. So when I was reading all the things which he published or the related literature, I came to know that similarity indices are frequently used to study coexistence of species for similarity of sampling sites. And I also read additional things Something like generally analysis of co-occurrences enables us to distinguish generalist species that survive in broad range of environment from specialists that only strive in few localities. And additional things were that given two presence and absence vectors yi and yj of length m that represent two different species, the Jaccard similarity coefficient is used, which is nothing but ratio of their intersection to their union. Let us use this Jaccard index for data mining, which the topic which we are learning now. So Jaccard similarity is one of the similarity measure which is used in asymmetric binary attributes and for numeric attributes too. We shall learn it later. Let's learn initially for asymmetric binary attributes. So Jaccard similarity, which is also known as intersection over union and is also known as Jaccard similarity coefficient, is a statistic used for gauging the similarity and diversity of sample sets. Jaccard coefficient measures similarity between finite sample sets and is defined as size of intersection divided by size of union of the sample sets. So this is a formula which is used for computing Jaccard coefficient or Jaccard similarity between any two sample sets. This is ratio of cardinality of intersection to cardinality of union of two sample sets. And we have to note that when both the sets A and B are empty, similarity comes out to be 1, and similarity always lies between 0 and 1. In case of pattern discovery, Jaccard coefficient is referred as coherence. We shall be learning this term also. And this formula, with the help of this Venn diagram, you can understand better. This is cardinality of intersection area divided by, we'll be using union of both the sample sets. So ratio of these two. This is one example where we are given two sets, set A and set B. In set A, we have 6 members, 0, 1, 2, 4, 5, 6. And in B, we have 7 members, 0, 2, 3, 4, 5, 7, 9. To compute similarity between two sets A and B with Jaccard similarity measure, we have to use a formula. Similarity between A and B is nothing but we have to take cardinality of intersection and cardinality of union and take a ratio of them. So how do we compute intersection? We are given two sets. So we can compute intersection of set A and B as set of all such elements which are present in both the sets. So 0, 2, 4, 5 are present in both the sets. So cardinality of intersection comes out to be 4. And union is nothing but set of all such members which are present in either A or B or in both. And as it is a set of unique elements, members which are present in both the set are listed only once. So cardinality of union comes out to be 9 and similarity 4 by 9 results in 0.44. So we also say that similarity between two sets A and B is 44%. This is another example where we are talking about biodiversity in two rainforests. And for computing similarity, here we are not given the species sets. Rather, we are given that the total count of these different species is 6, and there are two species which are common in both the rainforest, and we have to find out Jaccard coefficient. So here we don't have to count the cardinality of, or the set of intersection and union of the two sets. Rather, we are given. So when we substitute, we get 2 by 6, which is nothing but 1 by 3, and we say that there is similarity, or two rainforests are 33% times similar to each other with respect to the different species. One more example. Here is a table for 3 patients which we solved earlier, Jack, Mary and Jim, and these are the features given, where 3 features: gender, fever, cough, and then test 1, test 2, test 3 and test 4. Total 7 features for 3 patients. And we have to compute dissimilarity and similarity for each pair of the patients. For doing this, we know that gender is a symmetric binary attribute. So we have to consider only asymmetric binary attributes. So we shall be treating asymmetric binary attributes starting from fever, cough to 4 test. And here Y is nothing but we will be considering yes, that is positive, as 1 and negative as 0. And for P as positive again as 1 and negative N for 0. So we are given a table and we shall be computing distance between each pair of this. So values result in 0.67, 0.33 and 0.75 with our formula. How did we get these values? Let's see. So we have to construct again a contingency table for each pair like we did it for symmetric attributes. This is a given table. So excluding gender, which is symmetric attribute, we shall consider all remaining attributes, 6 attributes, which are asymmetric binary attributes. And let us construct contingency table for each 2 of these 3 patients. So for each pair, contingency table. So this is a contingency table for Jack and Mary. We have to construct this contingency table by counting all such values where value for Jack and Mary both are 1. So if you look at for fever, they both are having yes value, and similarly for test 1 both the values are 1 1, that is positive. So the count comes out to be 2. Similar to this, we have to compute for all the remaining attributes and fill up contingency table for each pair, that is these 3 tables we have to construct. And from these contingency tables, we have to compute dissimilarity between each. Note that for dissimilarity of asymmetric attributes, we don't consider the term, that is t, both values 0. So at denominator, you will realize that the count of 3 is missing, and we compute by adding these 2 values for where one of them is 1 and the other is 0, and that count is 1 plus 0 divided by 2 plus 0 plus 1. That comes out to be 1 by 3.33 is dissimilarity between Jack and Mary. Similarly between Jack and Jean, and then we compute for Jean and Mary. And this is a dissimilarity matrix for pair of 2, each 2 of the patients. So what we learnt was for symmetric and asymmetric binary attributes. We learned how to compute the proximity for symmetric and asymmetric binary attributes. We were constructing contingency table and we used 2 formulas where for asymmetric binary attributes we didn't consider the term where both the attribute values were 0 for 2 objects. And similarly we can compute for remaining objects. So from the earlier example we learned that between any 2 objects we can compute proximity. Simple matching coefficient is a term which we have to learn. One of the formulas which we used earlier, we named it as Jaccard coefficient. It was popularly known as Jaccard coefficient. Similarly, the other formula is simple matching coefficient. Let us see what is the simple matching coefficient. Simple matching coefficient is statistic used for comparing the similarity and diversity of sample sets. Let us consider 2 objects A and B with n binary attributes. Then SMC for A and B is defined as ratio of number of matching attributes to total number of attributes. And this is computed in terms of sum of M00 and M11 divided by sum of M00, M01, M10 and M11. What are these? Recollect the contingency table which we used earlier. This is similar contingency table for 2 objects B and A, except there we were writing column, first column with 1 and then 0. Here we are naming it 0, 1. This is why I said that in literature you may come across different notations. They all mean same. Just the order has been changed. Here we are using A and B. Sometimes we use object I, object J, and we were using terms Q, R, S, T. Here we are using M00, M10, M01 and M11. So simple matching distance can be computed with SMC. by formula 1 minus SMC. That is, subtracting SMC from 1 will give you distance. Let us understand few more things about SMC. You must have noted that in SMC it counts both mutual presences, that is attribute having values 1 1 as well as count of attributes with the values 0 0, that is both mutual presence as well as mutual absence, and it compares it with total number of attributes. In Jaccard index, we counted or we were referring to only mutual presence, whereas mutual absence was excluded. So formula SMC, that is simple matching coefficient for two objects A and B, is as this, that is we are treating both mutual absence and mutual presence. If we look at Jaccard similarity and simple matching coefficient, then we feel that they both are similar to each other. But the core difference is the term M00 is excluded from both numerator and denominator in case of Jaccard index. Or we can also say that where 0 and 1 carry equivalent information, that is if we have attributes symmetric, then we will go for SMC, whereas if we have asymmetric attributes where we do not give equal importance to both the values, then we shall go for Jaccard index similarity measure. Let us consider one example. We are given two sets X and Y with binary attributes represented in terms of ones and zeros, and we have to compute similarity with SMC as well as with Jaccard coefficient. So we know a formula for simple matching coefficient as this. So when we substitute values in this, we have to again construct this contingency table, where 1 1, that is value which is to be substituted here, is we have to count the terms where both the values are 1 1. So if you count, we will come to know that here is both 1 1 and here both are 1 1. So the count comes out to be 2. So F11, or you can use M11 any term where both the values are 1 1, both the values are 1, count is 2. Similarly, we'll count for remaining and substitute it in contingency table, and then substituting these values in formula, we get simple matching coefficient as 0.57. And for Jaccard similarity index, we are not going to consider this F00 at both numerator as well as denominator, and then Jaccard similarity results into 0.04. So if we use simple matching coefficient, we can say that set A and B, that is X and Y, are 57% similar, but whereas Jaccard similarity is going to say that they are 40% similar. Look at this example, which is similar. We will be constructing a contingency table, then we'll substitute the values, and then we will get SMC as SMC computed and Jaccard coefficient computed. What is exactly difference between both of them? Consider a supermarket with 1,000 products and 2 customers. In reality, at supermarket, we have millions of products and we have millions of customers. But we are now considering, for understanding difference between these two, what is Jaccard coefficient and what is SMC, or when to use which one, we are considering this example. We have 1,000 products and 2 customers. We are going to look at baskets of these 2 customers. First customer basket contains salt and pepper, and second customer contains salt and sugar. So if you look at the basket contents, you will realize that one particular item is common for both, that is salt. In this scenario, the similarity between the 2 baskets as measured by Jaccard index would be 1/3. But for similarity, that is SMC, it is going to be 0.998. 1/3 will result in 0.33 and SMC comes to be 0.99. So how come we are getting so much difference between 2 values? Here, out of 1,000 products, the basket contains only 2 products, and remaining product values are some attributes, something like where both the baskets are not containing them. So values are going to be 0 0. If we are representing these items with binary attributes, then 1 represents that item is present in the basket and 0 will represent item is absent in the basket. So in case of SMC, as we consider M00, that is where both the attribute values is 0 also, these remaining attributes out of 1000, excluding these 3, remaining all attributes will have 0, 0 for both the baskets. They are also considered. This is why similarity results in 0.99, where our Jaccard index is going to be just 0.33. This is because in SMC we consider the values where mutually both are absent and both are present. In case of Jaccard index, we consider only mutual 1 1. That is where item is present in one of them or both of them. This is why we should use Jaccard index, which is more appropriate in such case. Another variation of Jaccard similarity index is weighted Jaccard similarity. In weighted Jaccard similarity, we consider instead of 1 and 0, we consider a weights of these attributes, or this could be some numeric values. Given two sets, say x and y, with values x1, x2 up to xn, y1, y2 up to yn, with all real values xi and yi greater than or equal to 0, then Jaccard similarity coefficient is computed as jwxy, that is here, is equal to summation of minimum among xy divided by summation of maximum among xi and yi. This is named as weighted Jaccard similarity. And we compute distance, again similar to the earlier one. 1 minus similarity will give you the distance between two vectors. That is, these are the vector are the feature vectors. These are listing all attribute values for object y, and these are all attribute values for object x. And weighted similarity index is computed with this. This formula, if you look at this figure, is representing nothing but a overlap between two areas, that is intersection of two divided by union of two. This is Jaccard similarity index formula which we learnt, which was ratio of intersection to union. Let us see whether the formulas which we used, one was set notation, that is set overlap, and second is weighted Jaccard similarity, are giving us similar answer or are both working in the same way. Let's check with one example. Look at this table. We have 5 objects, that is 5 data tuples, and we have 4 features. These 4 features are 4 attributes, which could be 4 items for the supermarket. It could be item 1, 2, 3, 4. It could be bread, butter, jam, and something else. And to compute similarity between the two customers, say object 1 and 3, we have to look at the items they have purchased. So 10 may represent that the customer 1 has purchased 10 in quantity the item 1. To compute similarity between the baskets of customer 1 and 3, we shall use the formula for weighted Jaccard similarity computation. Here it is ratio of sum of minimum among the two attributes to maximum among the attributes, sum of all maximums. To compute the similarity between object and 1, we shall write the values of minimums at numerator and max at denominator. So if we look at feature 1 for object 1 and 3, it is 10 and 9. So 9 we write at numerator and 10 here. For feature 2, it is 3 and 4. So 3 at numerator, 4 at denominator, like this for all. And it results in 19 by 25, which is 0.76. So we say that there is 76% similarity between two objects, object 1 and object 3. These two formulas which we used were, one was set based Jaccard similarity and the other one is weighted Jaccard similarity. And this is the formula where we'll see that whether we use set-based approach or whether we are going for weighted Jaccard similarity index, they both work for binary symmetric asymmetric attributes as well as if we have weights to the attributes. So here we are given two sets, set A and B. We have already computed a similarity between these two using set-based approach, which is nothing but ratio of union to intersection. We took cardinality of intersection at numerator and cardinality of union at denominator, and it was 44% similarity. If we represent them, these are, if we look at all the digits which are present in these two sets, we can list them as 0 to 9. And then if we represent presence with 1 and absence with 0, see 1, 0, 1, 2 are present in set A, so all they are listed with 1, 1, 1. And 3 is absent in set A, so we represent it with 0. And now if we use weighted Jaccard similarity formula and if we list them in the formula, we will get a same value, that 44% similarity in these two sets, set A and set B. So what we learned today is computing proximity for binary attributes, whether they are symmetric or asymmetric. And I realized that often among students, they are not able to recollect and decide which formula is to be used for solving which kind of problems for given binary attributes. So I have just summarized them in a table. So prior to that, let us summarize in brief what we learned. So we learned how to measure proximity for binary attributes. And we learned two techniques, that is two measures, popularly known as simple matching coefficient and Jaccard similarity coefficient. And we have to go for symmetric binary attributes using SMC, and we have to compute asymmetric binary attributes proximity using Jaccard similarity coefficient. This is a table where we can list all the formulas, all the measures which we learned today. This is a contingency table which you have to fill in first for the given values, and then proximity measure for binary attributes is to be computed based on whether it is symmetric or whether they are asymmetric. If the binary attributes are symmetric, then you have to go for simple matching coefficient to compute their similarity, and the formula is M00 plus M11 divided by sum of M00, M01, M10, M11. That is nothing but we are taking sum of count of all the attributes at denominator, and at numerator for symmetric attributes we consider where the count where both the values 0, 0 and both the values are 1. And when we are computing distance, we consider either of them as 1 or either of them as 0, that is r plus s divided by sum of all. And if we are considering asymmetric binary attributes, then we use Jaccard index for computing similarity. And distance is 1 minus similarity, which results in this formula. And note that at Jaccard similarity index, we don't consider t, that is we don't consider this M00. This is omitted and it results in this formula. So very easy to remember. You can remember one of them, either similarity computation and distance formula can be computed by 1 minus, or you can compute one of them and then the distance, that is similarity, you can compute and then you can compute distance matrix. And we have also learnt about set-based and weighted Jaccard similarity formulas, which is ratio of cardinality of intersection to cardinality of union for the set-based approach. And for weighted approach, it is summation of all minimum values at numerator divided by summation of all maximum counts for all attributes. These are few assignments based on what we learned today, and you are supposed to solve this and submit. You have to post it, you have to at our Google Classroom, or you can mail me. And in next lecture, we shall learn about how to compute proximity for ordinal attributes and numeric attributes. This was all for today's lecture. Thank you very much.